So these advanced integration techniques are where our regular integration techniques and our new substitution method don't quite work. So things are close to looking like something we would like, but it doesn't quite line up. So for this first one, what we're going to do here is we're going to notice that this looks like one of our integrands. In particular, we have 1 over the square root of 1 minus x squared. Life would be good. Because if you have your purple sheet and your list of your integrands, right, that is sine inverse. But it doesn't quite work out because there's that 4. So this technique is, how do we algebraically manipulate this to make it look right? So you have an integral that's 1 minus x squared. So what we do is we say, well, if I want to make that a 1, does it make sense that I'd have to factor a 4 out of that? And if I factored that 4 out here, so here it is on the right-hand side. If I factored that 4 out, well, the square root of 4 would come out as a 2 in front. And if I had a 1/4 x squared, I could rewrite that as 1/2 x squared. So what I'm trying to do to manipulate it is, instead of having 4 minus x squared, I'm trying to get it 1 minus something else squared. Then if I have 1 minus something else squared, I could do a substitution. I could make the u equal to the 1/2 x. The derivative would be, du would be 1/2 dx. In other words, that dx by itself oh no, the half is actually there. I don't even have to do that. Sorry. Because we have the 1/2 already built into the equation. So now when I do this substitution, I get a nice clean sine inverse integral. The 1/2 went away with the dx to just be du, and the u substituted in there. And then we get our sine inverse plus c, and substitute it back, we have sine inverse of 1/2 x plus c. These algebraic manipulations do show up a fair bit with the inverse ones, because the inverse ones can be close, but with a number different. So first of all, in our head, we have to have, and really only have to have the inverse ones from the front side of your paper memorized well. Because the ones on the back side that are on the purple paper for inverses are just the same as the front side with a negative. So you can just use the front side and adapt with the negative as needed. So the ones that we have, right? Here's sine inverse. Tan inverse on the bottom has 1 plus x squared. And secant inverse has x and a square root of x squared minus 1. So those are things that you're looking for, the basic format with numbers changed. So this next one. Maybe. Maybe not. There. Oh. This next one, I have something plus something x squared on the bottom. I'm going to think about that. 1 plus x squared, because that's my tan inverse. So what can I do? Well, if I want the 1 plus, I'd have to factor out a 9. Doesn't look very pretty at this moment. And then if I want 1 plus something squared, Then I have to take that part and say, is it possible for me to write that as one thing squared? And sure enough, 4/9 is 2/3 times 2/3. So I get 1 plus 2/3 x squared. I rewrite it like this, and then I notice that if I make a u substitution for that 2/3 x, then life can be very nice. In this case, I got this, the dx by itself. So I'm going to have a 1/9. I'm going to have a 1 plus u, and then the dx is going to get substituted for the 3/2 du. I can pull the 1/9 out in front. I could pull the 3/2 out in front. Pulling the 3/2 out in front would give me 1/6, and I have a straightforward tan inverse. Substitute back. So the biggest trick to integrals is really knowing our derivatives well, because we have to be able to recognize things. First of all, if you have a straightforward derivative that you recognize, perfect, your integral is easy. Then, sometimes you have substitution. So I would look at this 9 plus 4x squared on the bottom. If I had an 8x on the top, this would be a substitution question, because I would look for a derivative inside my question for substitution. If that's not the case, substitution directly wouldn't work here because I don't have a derivative with x showing up. Then I start to look for those inverse functions. Does it look somewhat like this? Could I manipulate it to get that algebra? Sometimes we will also have to unadd fractions. So the square root of 1 minus x squared I see on the bottom. That makes me think of sine inverse. But I have an extra x on the top, so it doesn't work out nicely, because sine inverse would just be the 1 over the square root of 1 minus x squared. Just having the x on the top, that's a regular substitution kind of question, because the derivative of the inside function is 2x. So I have a regular substitution. If I take this and unadd the fractions, by unadding the fraction, we'd have the 1 over the 1 minus x squared minus the x over that. We can split this up into two separate integrals. The one on the left is perfectly sine inverse. The one on the right, you could use substitution because the inside function, the derivative is there. So if I let u equal the inside function, I take the derivative, I get negative 2x dx. That means I could get the negative x dx by itself by moving the 2 over to the other side. So my first one, perfectly sine inverse of x. My second one, substitute the u. It's a simple add 1 to the exponent and divide. Plug x back in. I like the way that sounds. Unadding fractions strategy. You break up your equation into two separate things. And a lot of integration, which is why lots of people find integration frustrating, is because you have to use creativity in math. Throughout your whole math, you've always had fractions, you need to add them together. Unadding them seems like you're working backwards. But in this case, it's what's needed to figure it out. So how do you recognize when maybe you should use an unadding fraction strategy? Because what's going to happen on a test or on your exam is you're going to get an integral, and it's not going to be based in, oh, we're learning this in the advanced techniques, so my brain is thinking advanced techniques. You're going to have it in the midst of, here's everything you've learned so far. Can you do this question? And you're going to have to go through all of your strategies. So I'm going to just talk about how I would look at this question and how I would probably try things first that wouldn't work. Okay? I would look at this question and be like, oh, okay? So first of all, you get an integration and you're like, oh, because I don't see how to do it right away. And most likely I would go, all right, probably it's substitution. So I let u equal 4 plus x squared, and then du dx is 2x, and then I'm like, oh, there's the extra plus 1. If that plus 1 wasn't there, this would be the strategy, and it would work. But the plus 1 is there, and this strategy now doesn't work. Integration is a very fine line between having something, an integral you can do, and having an integral that's actually impossible to do. And that's really bothersome for math students to have there are some integrals that you can't do. And some of you found those, like you said, that name of that function that had to be found out to do that one on the test. That was a calculator question. There was actually no way to do that integral with any of the math that we know. So we try something, it doesn't work. Okay? Then I would look at it again and go, oh, all right. Well, the bottom is a 4 plus x squared, which is close to 1 plus x squared, and that would be my tan inverse integral. So maybe this makes sense to unadd the fractions. If I unadd the fractions, this is really nice because I already found out that's what I would need for my substitution. So even though my first technique that doesn't work, it gives me a hint of something later on that might work. If I break this up, I'm like, hey, this one's going to work out nicely with substitution. And then I get the plus 1 over, and that might work out really nicely for tan, but I need a 1 plus. So then I'm thinking about that 1 plus 1. I'm like, okay, well, if I factor out the 4, I could rewrite the 1/4 x squared as 1/2 x squared. And now I have this broken up. This one I can use the u substitution. And this one, I can rearrange it with the 1/4 out in front. And if you used U substitution here and you want to do another substitution over on that one, you're going to have to introduce maybe W. Right? If you wanted to do that substitution, I'm not going to uncover the boxes, but here we have u to the -1, which is your natural log. So you're going to get, I'm not going to uncover these, I'll just work from here. I'm going to get natural log of the absolute value of u plus 1/4, and if I do the substitution here, I'd have 1 over 1 plus w squared and 2 dw. I can substitute back in and actually notice here u was 4 plus x squared. You see, I took away the absolute values because 4 plus something squared is positive. So I don't need the absolute values. If you had left them, I don't think they would take off any marks. Just absolute values and things look more awkward for typing into a calculator later on. So it's kind of nice that we don't need them there. The 2 and the 1/4 is going to become a half. And this is tan inverse of w, which I can substitute back to 1/2 x plus c. That is advanced technique number 1. Recognizing one of your tan inverse ones that's close, but doesn't quite match up. Using some skills of factoring. And all the inverse ones involve a 1, so you usually have to factor out the number to get that 1. Also the strategy of unadding the fractions. So if you've got a fraction that doesn't match up with regular substitution, that this one does, try breaking it up, and then you have 2 integrals to do instead of 1, but it might be possible.